Hey guys, welcome to our next lesson. A lot of the problems we've been solving lately have kind of been leading into this topic today. So today we're going to be talking about solving systems, and you're going to learn what that is, and there's a specific method we're focusing on today which is called substitution. Our mindset message for today is to find the beauty in math. Remember, math is such a beautiful way we have to express how everything works in the world around us, but also just to share ideas about numbers and shapes and all sorts of other things. And in general, it's all about patterns, and I think that's beautiful, and I think our topic today actually really is a cool way to show patterns using all the things we've been learning with graphing and equation solving and all of that stuff. Our main learning goal today is to solve what we call a system of equations by the substitution method. Prior knowledge, basically we need to remember about graphing lines, that will be helpful, as well as just solving equations using the basic moves of algebra. The first thing we need to do today is actually define what is a system of equations. Now first, let's think about the word system. When do we use the word system in everyday language? Generally, the word system kind of means, if you have a system for something, it means you have multiple parts or pieces that all work together. So a system of equations actually means multiple equations that we're trying to solve together. And here's what that means. So here's that definition I just said. What this really means is we're trying to find the point, or maybe points, that make both equations true at once. So we're trying to figure out a point algebraically, right? That's the main thing we're going to use today is algebra, that makes both equations true at one time. And if you find a solution point, that also represents a location where the graphs of the equations intersect each other. So where the graphs will cross. Okay? So understanding this will help us jump off into the rest of this lesson. Let's just dive in with an example to introduce this and then do some more practice. Let's take a look at a problem that might be familiar to you to help introduce this method. So let's say we have a gym that has two membership options, the basic and the ultimate. The basic costs $50 to join, but then $15 per month after that. And then the ultimate costs $10 to join, and then $20 per month after that. Clearly, which one's cheaper just to join? The ultimate, right? However, the ultimate is $20 a month, which is more than this. So eventually, even though that ultimate starts cheaper, as you go up, you can imagine the line of increase in cost. The ultimate will catch up somewhere, right? Now the only other difference between these two in this problem that we've talked about is that this just gives you access to one gym location and the ultimate gives you multiple gym locations you can visit. So for this problem today, we're going to kind of ignore the location part, which I know that does play into your decision. What if you want to be able to visit multiple gym locations? Then obviously that decides what you want to do. But if we just purely think about cost only, and we just ignore this piece of information, the question that we're going to ask today is, after how many months will your total cost be more for the ultimate membership? Like we said, it starts out cheaper, but its monthly cost is more expensive. So we know eventually it's going to catch up. So we're trying to look for how many months need to go by before that ultimate membership catches up. Well, the good thing is we can write equations for these two costs, and then we can use this new method we're learning to actually figure this out. So the cool thing is, when we have something in this structure where you start out with a certain amount and then every month or every day or every minute or whatever it is, you add or subtract a certain amount, there's a cool, easy thing we can do. So let's just start out with y and think of that as like our output, and that's going to represent the total cost. For the basic membership, we know that we start with $50 no matter what. And then how many months go by? Well, we pay $15 per month, and we're going to use X here to represent the months. Because depending on how many months, that's how many $15 increments that I have to spend, right? And then same for this, but this starts out with $10, and then it costs $20 a month to join. And so remember, the X here represents how many months have gone by. Now remember, we are looking for when they're going to actually cost exactly the same, because that's when the ultimate will surpass the basic, right? So if we're really looking for where the costs will be the same, what we're really saying is this y, we want it to be exactly the same number as that y. And since these two will be identical, really what we're saying is, when will this cost be equal to that cost, right? So this turns out to be an equation that's really important. If you have these both y equals, you can then say, well, I want both of these to be true and equal to each other. So I can make this equal that, and I have an equation. 50 plus 15x equals 10 plus 20x. And now I can just solve that equation using the basic moves of algebra and figure out x, which will tell us how many months need to go by for the cost to be the same. So I put this equation over here, and I just went through the basic moves. If you need a refresher for yourself or a reminder how to do it, you can. But in the end, when we solve this for x, we get x equals 8. And don't forget that stands for 8 months. So after 8 months, that's when the ultimate membership will become more expensive. But it's really powerful to have the tools of algebra available to us to solve problems like these. So let's jump into some specific practice purely just using this method. So we have two equations. In this case, we have equations that are solved for y, and we want to use this substitution method to solve them. I'm going to work through this one, part A, and share with you a little bit more. We didn't talk about where the word substitution comes from necessarily, but just think of it like this. Both of these expressions are equal to y, and that y is the same. So you can think of it as, well, since they're both equal to y, I can substitute one entire expression for y here, essentially making this and this equal to each other. Again, because they're both equal to the same thing. Does that make sense? So our first step for this one to solve it would be to say, well, then I know 1/2 x plus 5 must equal 3x minus 2. Again, because they're both equal to the same thing as each other. So it kind of links them together. And now we can just go about solving this. One reminder to give you for ones like this, especially if there's a fraction, you could certainly just go about it straight away by putting the x's and then the constants on one side on opposite sides. But I like to do a little thing here where if there's a denominator, I'm going to multiply everything on both sides by that denominator. It just makes the numbers easier to work with. So that's my choice. You don't have to do that. 2 times 1/2 just becomes 1. So that's just x plus 10 equals 6x minus 4. And now we can just finish solving this the regular way. So finishing this one off, again, I just went through the basic steps using the basic moves of algebra, and I got x equals 2.8, or you could write 14/5. For these purposes, I find it often easier to leave it as a decimal when I go back in here. But sometimes if you have a decimal that's not perfect, you may have to leave it as a fraction, like 1/3, because you can't put it perfectly as a decimal, right? Now, I've got x, but there's one thing we didn't mention in the last problem that's important. When we're solving a system, we don't just want the one variable, we actually want to know the value of the x and the y, because what we're really looking for here is, if you think of these as lines, for example, we're really looking for where those two lines cross each other. And that has to have an x and a y coordinate. So now that we found the x coordinate, we can go back and solve for the y coordinate. And you can plug that x into either equation that you want. I think I'm going to use the second equation because there's no fractions or anything to deal with. So if we take that 2.8 that I found for x in my substitution that I used, then I said I'm going to plug it into this. Again, you can use either equation because we made it so that it's going to be fitting both equations. And if you simplify that, we get y equals 6.4. So here's my coordinates. X is 2.8 and y is 6.4. Remember, this is the point that makes both equations true at the same time. And that also means it's where these two lines cross each other. Now it's time for you to go and do B on your own, and we'll check our work. So let's just check the solving for x here. Again, these expressions are both equal to the same thing, and so we can make them equal to each other in this case. And I chose to go about it in this way. Remember, there's many ways you could solve this equation, so just because you didn't do it my way doesn't mean you didn't do it correct. If you got x equals 3, that means you probably did it correctly. Okay? So you can look through my steps if you like, but in the end, here's what I get for x. And now let's plug that back into one of the equations to figure out the y. So I chose to use the first equation in this case. And if I plug 3 in for x, it says y equals negative 3 plus 3, which is just 0, because they cancel out. And so it turns out if x is 3 and y is 0, that coordinate pair makes both equations true at the same time. And again, that also means that's where those two lines cross each other. Let's look at a couple more examples of these that are slightly different because they're not just already solved for y or solved for x or something. So here's another system of two equations, and right off the bat you can notice that neither equation is set up in such a way that they're automatically already equal to the same thing as each other. So I cannot just make, one side equal to the other side and go for it. We're going to have to do a little bit of work first. Now, one thing you could do is you could just solve both of them for y, so they say y equals, so rearrange the two equations. You could also solve them for x if you wanted, but let me share with you probably the most efficient way of tackling this one. We're going to take the first equation and we're going to rewrite it using the basic moves, and I'm going to add 2y to both sides of the equation so that this one becomes x equals 3 plus 2y, and then the other one becomes 2x plus y equals 16. And we're going to leave this other one. It's actually enough information if just one of the equations is solved for one of the variables, because watch what we can do with it here. Because we realize that this expression 3 plus 2y is the same as just x, it means that this expression can be used in place of x anywhere else. So if you see an x somewhere else, you could replace it with 3 plus 2y. So look, there's an x right here. So that x can be replaced with 3 plus 2y. And what we've done is we've made this become an equation that only has y in it, and we can solve it for y. So 2x plus y equals 16, so we have 2 times x plus y equals 16. And that's just because this is the same thing as x. So now we can just simplify this side and solve the equation. This becomes 6 plus, distribute that, 4y, plus another y equals 16. And these two can be combined together, so anytime, remember, that you see like terms, you can add or subtract them. So this becomes 6 plus 5y equals 16. And at this point now, all we need to do is backtrack it. So finishing these steps, if I subtract 6 from both sides, I get 5y equals 10. And if 5y equals 10, then y must equal 2. So we've got the y coordinate where these lines cross each other, but we got to still figure out the x. So let's just go plug this y. That'll be nice to use this equation. We'll plug y into here to find our x. So using this equation, again, it's already solved for x, so it's really an easy one to use to find x. And 3 plus 2 times 2, because that's what we got for y, and then we get x equals 7. Therefore, my final answer to this equation, to this systems of equations, the solution to the system is this coordinate pair 7, 2. Now let's have you try a similar one on your own. So remember to follow the steps carefully of the last one. We'll stop partway in just to check that you've set it up correctly. So let's make sure that you set this up correctly, okay? The easiest way to solve here is solving this equation for y. So we'll subtract 2x over there, and we'll rewrite the system so y equals 7 minus 2x is on top, and we left the bottom one the same. Now this can always be substituted anywhere you see a y in this case. So here's a y in the other equation, and we can replace that with 7 minus 2x. So 5x minus 3y equals 1. And now here's an equation that only has x in it. So don't forget there's like terms here, which makes that a 11x. So I have negative 21 plus 11x. Solve that. X is 2. If you plug that back in, again, this would be the easiest one to plug in directly to get y. We get that y equals 3, so check your work on that. And my final answer is that x is 2 and y is 3. So this is the coordinate pair that represents where these lines intersect each other. And those numbers are what make both equations true at the same time. So this last question here that we're going to talk about focuses on something we should always be thinking about. If we're trying to solve something, you should always ask yourself the question, is it always possible to solve? It turns out, I'll give it away, this one has a problem with it. Okay? So what happens when we solve this system? Luckily, this is one of the easy ones. They're both already solved for y, so we can make this equal to that. But if you see this, we get 3x plus 4 equals 3x minus 1. And you may be able to remember when we did equation solving that we could just look at this and we can know that there's a problem, there's no solution. You could also realize if you try to subtract the 3x from both sides, it cancels out on both sides here. And what we end up with is 4 equals negative 1. And we know that 4 is never equal to negative 1. And so our conclusion to this problem is that there is no solution. Now let's remember, we're trying to find where the lines cross. If there's no solution, that means the lines don't cross. So important thing to mention here is that the lines don't cross. Now there's something very important about these equations based on those lines that tells me, oh, I know that they won't cross. But we're going to end up getting into that in our next lesson. So that's it for this lesson today. Again, happy math, and we'll see you guys next time.